Thank you so much for coming, everybody. This is our second workshop of the quarter. Today we're going to be covering mainly strings and arrays, some other topics that are related, and a few example problems. Here's the link to the slides. You can see it up there, bigger, and it will be at the bottom of the presentation the whole time. So if you ever need the slide link, you can go right here and find it. Let's get started. Can everybody see everything okay? It's all good? Okay, sweet. So first up, we have a raffle. Every week, the contest is your chance to win an Amazon gift card. For every problem you complete, you get one entry into our weekly raffle. And so let's go ahead and do this week's raffle and see who is our lucky winner for an Amazon gift card. Congrats to Santiago. Santiago here today? No? Okay, well, we will email them with their rewards probably at the end of the quarter. We'll just do everything at once, but make sure to do the contest problems. All the example problems and the real problems are entries. So just by participating in the workshop and doing the problems during the week, you get a chance to win a prize. So can you write that down? Okay, so on the agenda for today, we are going to cover arrays, the 2D arrays, vectors, strings, including characters, and then we're going to go through these three example problems, Patuljci, Disastrous, Downtime, and if we have time at the end, we'll also cover Bologna, but we will have a Kahoot in between. Yeah, so let's get started. So we want to talk about these three major data structures that you will see in competitive programming all the time today. Maybe you're already familiar with them. If you are and you're getting a little bit bored, you can try working on some of the contest problems, but we're going to go through a lot of the basics of arrays, vectors, and strings, particularly in C++, just so you all know how to use them in competitive programming problems. Starting off with, an array is a data structure that holds elements of the same data type. We went over them a bit last week, but just to make sure that we're covering all our bases, we're going to go in depth today and talk about exactly what it means for an array to exist in C++ and just in general. As you can see here, there are a couple examples of arrays, integers, booleans, and characters. What's important to recognize is that all arrays have the same data type within them. So you cannot have an array that has both integers and strings and characters like on the left here. Arrays are just meant for storing the same data type contiguously in memory. In C++, the way that we declare an array is by declaring the data type for the array, and then giving our name, and then declaring the size of the array in brackets, and then you can immediately set the elements of your array as so, and that will give you this representation in memory just by doing a declaration like this. You could change that 5 to a different number to make it bigger or smaller, and you can change the values if you want. And when you want to access these elements in memory, you use this bracket notation in order to index into the array element that you want to pull out and use as a value. So if you're ever confused about exactly how that works, in C++ and all languages, arrays are zero indexed, meaning that the first value is the 0th element, and you will have to use brackets and 0 in order to access it. And then from then on, it counts up as you would expect. And if you don't know what values you want to put in your array right away, then you can just declare one and it will have uninitialized values. And so you can use a for loop or some other mechanism in order to fill in the values as you go. But just know you don't have to set the values immediately. You can do this and then replace them later and access them. But just make sure that you're setting all array values before you try to access them. Otherwise, you'll get random data. And that's no good. Two-dimensional arrays work exactly how you'd expect. Instead of using a single bracket, you use this double bracket notation, both for declaration and access. And it kind of just creates this matrix idea. It's still a contiguous segment of your memory, but it's represented in your head and in your code and your writing as this 2D structure where you have a certain number of rows, a certain number of columns that can each store a different data point. And when you want to access a value, again, both sides are 0 indexed, but you just want to go to the column, the row number, and then the column number using brackets, and you can pull out that value from an array. And to declare it, it's the same as single dimensional arrays, you just need this 2 bracket notation, you need the size, and then you can go through and you can change values, access them, do whatever. Does anybody have any questions about arrays? So if you don't know exactly how big you want your array to be, you'll notice that that is kind of an issue, because for array declaration, you need to know the size as you're inputting your name and declaration. And so in most languages, we have this tool called a vector, which lets us deal with arrays of varying size. You don't need to know exactly how big it is when you create it, and you can add and push elements to it as you go. And in order to use vectors and get this functionality of having a varying array size, you just need to include #include vector at the top of your program. If you're using bits/scdc++, then you don't need to use that if you're on Windows. But let's just talk a little bit about vectors. So to declare a vector, after you do that include statement, anywhere in your code, you can declare a vector by stating this keyword vector in those angle brackets and including the data type in there, and then saying the name of your vector. And that will declare a new empty vector, which you can add elements to. Just know that there'll be nothing in it when you initialize it, but there's an example of how you would declare in a vector. And it's kind of just like an array. It has some more functionality. For example, if you want to set all of the elements in your vector to a certain value and you want to declare its size, its creation, you can do so using these parentheses and these 2 values here, size vector and the initial value of elements. So if you wanted to create a vector that has 5 instances of the integer 100, you could do that using vector int hundreds 5 column 100. So if you have any questions about that, just remember to go check out these slides. Vectors kind of work the same as arrays in C++. You can access the elements inside of a vector using that same bracket notation and the index of the value that you want to pull out of memory. And you can set them in the same way. So by creating a vector of 3 elements, a Boolean vector, and then setting the second element, or really the third, to true, you get something like this. So in this way, they're kind of similar, but they add all sorts of functionality, which is sometimes really key for completing certain competitive programming problems. If you want to see a quick reference sheet with some of the most important vector functions and operations, here's a quick cheat sheet. You can go to the reference page online and see a full list of member functions for vectors and all the possible operations that you can do with them. But here's a quick rundown. The main ones that you'll probably end up using are vector.size, which gives you the size of a vector. So that kind of gives you like your typical end value for how big your vector is if you aren't aware at the time when you're using it. You can get the front element and the back element by using .front, .back, don't forget the parentheses. And you can check if your vector is empty or of 0 length just by doing this .empty command very quickly. The way that you typically would add elements to a vector is by using this vec.pushback command, and then you insert the value, and that automatically adds it to the end of your vector and increases the length of the vector by 1 accordingly. There's a lot that happens internally in C++ and other languages to make that happen, but you don't have to worry about that as a coder. All you need to know is that the vector automatically resizes to the size that you need. Same when you do insert, which allows you to insert an element at a certain position in the vector just by knowing the index that you want. And same when you erase, you can either erase a single position or a range of positions. And when you do that, it will automatically resize to the new necessary size once those elements have been erased. Does anyone have any questions about vectors? Okay, great. Last up, we're going to talk about strings. Hopefully you're familiar with them, so we did use them before, but a string in C++ and other languages is a data type that represents a string of characters. So you can use it in the same way like you'd use other data types just by declaring it, and they're actually pretty similar to arrays in C++ as they're represented as arrays of characters. They're not a primitive type though, so you need to include this #include angle bracket string in order to use them in your program. So just don't forget, if you're using strings to do this, if you're using vectors to include vector, so on and so forth. To declare a string, you just do the same thing that we've been doing. The data type, now named string, the name of your string that you want, and then you set it equal to something in quotation marks in order to make that a string. And when you want to declare a character, just a single character, you can pull one from a string by accessing the index of the character that you want and the string name using those brackets in order to access it. And then you can set it equal to a character using this data type keyword tar. Here are some common string operations, kind of similar to the vector ones. You got .size or .length, which will give you the length of your string or the number of characters in it, including white space. Either of them work. It doesn't matter which one you use. You can push back characters to the end in the same way that you would with the vector, but a lot of times what you end up doing is probably just directly concatenating two strings together using the plus operator. This will automatically tell C++ that you want to concatenate these two strings, aka add one to the end of the other, and it will do that for you just by giving it two strings, adding them. They can be variables, they can be direct literals like this, doesn't matter. There are a bunch of other useful string operations that you can find on the reference page. A couple ones that you might use at some point is alnum and toUpper. Respectively, those return true if the character at the given index is a letter or number. So you can check if the characters in your string are alphanumeric or if there's special characters. Sometimes you'll need to check input in problems. And toUpper is a function for strings that will capitalize a character if it is lowercase, otherwise leave it alone. And there's a lot of similar ones, like checking if something is white space, putting something into lowercase. A lot of useful string operations. Many times you just want to lowercase a whole string, so maybe you'll iterate through it and to lower every single character. So those are some examples, but if you need to use these functions, don't forget to check out the reference page where they have all of the information, all the details, and all the other functions that you could possibly use. So in C++, in general, every single character has an ASCII value associated with it. This is just a universal code that we decided upon to represent each character in the possible language of anyone using numbers in our computer. And hopefully some of you have heard of ASCII before and are a little bit familiar with it, but just to run through it quickly, let's just do a quick quiz about how this works, or first a quick explanation. You can go down to the character column and find the character that you want, and then you can find its ASCII representation in memory by going over to the decimal column and just pulling that value directly. So in this case, you can see that capital R is represented by 82 in ASCII, and lowercase r is represented by 114. So just a quick quiz. Can anyone tell me what the ASCII value of lowercase b is? 118, fantastic. And can anybody tell me what the ASCII value of 7 is? 55, nice. And notice that just because the character itself is a 7 doesn't mean that the ASCII value is a 7. They are not correlated. It is just a one-to-one mapping of characters, whether it be white space, special characters, numbers, letters to decimal values. And this is the table, universal. You can look it up online. You can look at the slides, but this is where you will find that comparison. So characters can actually be pretty useful for some fun competitive programming strategies. The way that we use these characters is typically via their ASCII values, which is why we're going over this. And in C++, especially, characters are automatically cast to their ASCII value when you need to use them as an integer. So what this means is that if you take a string and then you take a character from that string using the bracket notation, it will give you that character value. But if you perform a non-string or character operation using that value, such as adding 1 to it and treating that character as an integer, C++ will automatically cast the value of the character to its ASCII value. And in this case, capital I turns into 73, and you add 1 to it, and it will give you 74 instead of a different character. And this can be particularly useful when indexing into arrays. So you can use a character as an index value just by putting it inside these brackets, and it will automatically convert to its ASCII value, and you can use that as an array index. And this is particularly useful when you subtract other characters from the character value that you're trying to use as an index. So here, by taking the lowercase letter c and subtracting lowercase letter a, since A is the first letter in the alphabet in the ASCII table, subtracting lowercase a from any other letter will give you kind of its position in the alphabet. So here, C is 99 and A is 97. So by subtracting them from each other, you get 2, which is to say that C is the kind of third element in the alphabet. If you count A as 0, B is 1, and C is 2. So sometimes this can be really useful for trying to count how many occurrences of each letter you have in a string maybe, because you can directly access the array indexes for an alphabet representation by using a trick like this. Okay, does anybody have any questions about how we use characters? Okay, cool. So let's get into our first example problem for the day. Here is the link to the Caddis contest. You can go to the slides, click on it directly, just type it in, open.caddis.com/contest/log2im. And once you get into the contest, open up problem A, Patuljci, and I'll give you guys just 30 seconds or so to do that. Make sure everyone is in before we get started. And I'll give you guys a couple minutes to read through the problem statement and try to understand what this problem is asking. And if anybody needs help still creating a Caddis account, if they weren't here last week or just getting into the contest, just let me or any of the other officers know and we will walk around and help you guys. That's fine. No, please. You guys are free to come and go as you want. Just as long as you're here, we appreciate it. Okay, so hopefully you've had a minute or two to read through the problem and you're starting to get an idea of how you might go about solving a problem like this. Let's just look at the sample test cases to get a better idea of what's going on. So basically, to sum up the problem, you're given 9 numbers as input, which represents the hat numbers of 9 different dwarves that have showed up to Snow White's dinner. There are 2 imposter dwarves among the 9, and Snow White knows that the 7 true dwarves have hat numbers that add up to 100. And she's trying to identify which 2 dwarves have snuck in to her dinner party. And so our job is to take the input of our 9 hat numbers and then give the 2, or find the 2 which are not belonging, and then print out the remaining 7. So in this case, if you go through the numbers in the sample output, you'll see it add up to 100, and there are these 2 other numbers, 25 and 15, in the input, which are not included because they go past that limit of 100. And so hopefully this is giving you a couple ideas about what we're looking for in this problem. So maybe take like a minute and a half, and try to just devise a non-code solution to the problem. If you were to just write out your answer to this on a piece of paper, what would that be? Okay, now that you guys have had a couple minutes to work on it and try to devise a solution, hopefully you made some progress and you're trying to get an idea of what might be the best way to go about solving it. Just to give you a good starting point, let's just talk about exactly what we're trying to find here. So we know that the true 7 dwarves values on their hats that were given as input sum up to 100. And then there are 2 dwarves whose values go beyond that value of 100. So intuitively, what we want to find are the 2 dwarves whose values sum up to this number beyond 100. So if you take in all of your input, here's a good starting point for reading in your input. You can find the sum of all of the input values as you go. And we know that our target, or the true value of these 7 dwarves, is going to be 100. And so our target, what we want to find, is the 2 dwarves that add up to the sum of everything minus 100. So by going through the input, getting it all and summing it up, and then subtracting 100 from that value, we get this value that we're looking for. And then our job is to identify which 2 dwarves give us this value when added together. So before I give you guys the final bit of the code solution, I'm gonna give you guys a few more minutes to work on it. Here's their key information here. As an example, the sum of this array is 173, and if you subtract out 100, it gives you a target of 73. And your goal would be to somehow go through this array, which you're given as input, and then find out which 2 dwarves have a value to add to that target, and then print out every single one in the array in order except for those 2. So take a couple minutes and try to code the solution to this. You can submit it on Caddis and try to get accepted. And let me know if anyone needs any help setting up their environment, doing anything Caddis or REPL or Xcode, VS Code related, and go ahead and try to solve this. And if you get done early, see if you can try to find another solution to the problem that's a little bit different. We will go through an alternate solution after this one, or you can work on the other problems for the contest starting from the fourth one. Okay, sorry to interrupt you all. I know you're diligently working, but let's just go through what a potential solution to this problem would be. The main part of our solution is really just this one block of code here. So the simple brute force solution that I was trying to guide you to and that you hopefully were able to find is that if you just iterate through every index in the array, and then for each one, iterate through the rest of the positions in the array, and check if those two values pointed to by your indexes add up to the target, then this third for loop goes through the whole array. And as long as you are not pointing at two doors which are imposters, which you've identified using these for loops and these indexes, then print them out. And so this is essentially saying, check every single combination of all the doors. So for each one, check every single other one and check if added together they equal the target. And if they do, then you know that those two are the two that you don't want to include and you should print out everything else. Does that make sense to everyone? Does anyone have any questions about that? Okay, sweet. So you can put this in on Caddis and try to get an accepted solution, but we're going to talk through another way that we can also approach this problem. So this is a good enough solution. It's perfectly fine. For this problem, we're only given exactly 9 values as input. It's not changing. And so we don't need to be super efficient. We don't need to worry about how long our solution is taking. But if you really wanted to be efficient and do the best possible solution, there's actually a different approach that you could use. There's often many different solutions to problems, especially as they get more complicated or advanced. There's many different ways, many different algorithms you can use to solve the problem, and some of them will be efficient, some of them will be memory efficient, some of them will have some flaws, simple things like that. And they all will work, but sometimes you want to find the best solution, and certain problems will require you to find the best one by limiting your runtime. And so instead of using brute force, there is a kind of better way to go about this. So our first job would be to sort the array to make sure that all of our input values are given to us in order of least to greatest. And then you can take 2 pointers or just indexes to the first and last value of the array, and then you can move them until you find your target value. Now I'll explain that using a quick graphic. And this is known as a 2 pointers technique. It's a common CS solution to a lot of these simpler problems, and it's used on a lot of more advanced problems as well. So to give you an idea of what I'm talking about, here's an example array. It's already sorted. You can use that. You can do that using just a sort function in any language. Super simple. You can take your input and just directly sort it. And here in our array, the sum is 123. And that means that our target value would be 123 minus 100, or 23. So we're looking for the 2 dwarves whose hat values add up to 23. So if we look at our first 2 values, pointed to by the left and right sides of the array, you can see that they add up to 28, which is too big. But if we move the right pointer in 1, then you'll see that because our array is sorted, that naturally decreases the sum. And so by moving the right pointer in 1, we get this new sum of 27. This is still too big, so we do the same thing again. We need a smaller value. We know that the array is sorted, so we're not missing any possible in-betweens. And so we just move that right pointer in 1 more value. And then you'll see that we end up with a new sum of 22 for these 2 dwarves. And now we've gone too low. So because we have a sorted array, we need to add a little bit of value. Let's move our left pointer up. You'll see that we get to the 5 there, and when added together, we went too high again. So we're kind of going back and forth on either side of our desired target. But if we move our right pointer in 1 more to decrease the value, we get back down to 22. And then with one last movement of our left one up, we get to 23. And so this is another way to find the solution. The code is a little bit more complicated for this, so I'm not going to go through it directly. If you want it, it's linked on this slide. Does anyone have any questions about the 2 pointer solution and how that works? Okay, cool. You can try to implement that this week if you want. It's a great exercise. It's very useful in a lot of other problems, but it's not necessary for this one. Just wanted to introduce the concept. And now we'll move on to our second example problem of the day.
Okay, so for example problem 2, we're gonna talk about like this problem called Disastrous Downtime. Very, very nice alliteration. So if you go to it's the same contest link, and then just click on the second problem, you would be able to see this problem. Yes. Now here's the problem statement, and then on the right I have a TLDR. But I would encourage you to read through the problem to understand what it's talking about. I'll give you guys, since the problem statement is really long, I'll give you guys like 5 minutes. And it's an interesting problem. I like it a lot. So has everyone gotten a chance to read through the problem already? Is there any questions? Like, is there anything you don't understand? Feel free to ask. So as a recap, basically, you are setting up servers for your company, and then your clients, well, each server machine can handle up to K requests at the same time, and then your client is gonna tell you exactly when they're gonna send you the request. Each request takes 1,000 milliseconds to process, and basically you have to start processing this request immediately as you receive the request. And the question asks you how many machines, like what's the minimum number of machines you need so that your machines don't crash. Basically, you want your machines to be able to process as like so many requests at the same time. Now, let's take a look at simple test case 2, right? The first line of input tells us there's going to be 3 requests, and then each machine is going to be able to process 2 requests at the same time. And after that, the following 3 lines tells us, exactly when are we going to receive these requests, right? At the bottom, I made the graphics, a graphic that shows this exact situation. So at time 1000, we're going to receive the first request. At time 1010, we receive the second request. So from 1010 to 1999, we are like processing 2 requests at the same time concurrently. And at time 1999, a third request comes in. And like notice that during this period of time, we need to be able to process 3 requests at the same time without having our service crashing. So the maximum number of requests that are being processed concurrently is 3. And then each server machine can process 2 requests at the same time. So it means that we need at least 2 servers to be able to handle this request load. So here, so like once you see the problem, once you see the simple test case, right, you need to come up with an idea to approach this problem. So what was the thing that we paid attention to when we were looking at the simple test case? It's this middle part where like all the requests overlap, right? So essentially, this problem is asking you to find out how many requests are being processed at each given time. And then like, we want to find the maximum number of concurrent requests at any given time. And then we just divide that number by K. That's the answer we want. So with this idea in mind, I encourage you guys to think about like a solution to this problem. Like how would you approach this problem? How would you code this using C++ or Python or whatever language you like? Take some time to try and see if you can come up with some solution. I won't give you like 10 minutes because it's kind of hard at the beginning if you don't know like how to approach it. So maybe like take 2 or 3 minutes to think about it, and then I'll keep going. Okay, so hopefully you had some time to think about it, like maybe come up with an idea or 2. And like basically this problem, well, here's this first solution. We're gonna talk about like a slightly easier solution first, and then we'll go into a better solution later. So the most easy to come up with solution is that you declare a vector called time, or like an array of time, and then each slot in the array corresponds to 1 millisecond on the time, right? Because the request can only come at like integer time, integer milliseconds. So you don't really care about like the interval between, like, let's say 1999 and 2000, and that's why we can use a discrete data structure to store a continuous idea, like the timeline. And then after that, we want to find a way to populate the time array so that at each slot, we know exactly how many requests need to be processed. At each time step, how many requests do we need to process? Here's a simple idea, right? Initially, let's initialize the array to all 0, meaning that let's suppose that it takes 3 milliseconds to process each request. Because 1,000 milliseconds is too much, so I can't really animate that number. So let's suppose it takes 3 milliseconds to process a request. And then let's suppose that requests come in at time equals 0, 1, and 2. Initially, there's no request issued by any client. So our timeline is clear, like we are free, right? So everything should be 0 initially. And then after we receive the first request, notice that the first request comes at time equals 0, which means from time equals 0, 1, 2, like in these 3 slots, we need to process this first request. And then the second request comes in at time equals 1. So that's why we need to increment the second slot, the third slot, and the fourth slot, and so on. Similarly, we need to increment the third slot, the fourth slot, and the fifth slot for the third request. And now if we look at the final array we have, our timeline basically, we notice that when t equals 2, we need to process 3 requests, and that is the maximum number of concurrent requests we need to do at any given time on this timeline. And that's the number 3 we want to find. And to get the answer, we just need to divide 3 by k, and then that's it. So here's the implementation for solution 1. I included both C++ and Python solution. So if you're interested in it, you can take a look and then maybe submit it on Caddis just to see that it actually passes. Now, let's analyze our solution, right? Solution 1 passed, but we got lucky. So for each request, we need to execute 1,000 addition operations. Because each request is 1,000 milliseconds long, we need to go through each one of the 1,000 slots to add 1, right? And this, if you look at the problem statement, there can be up to 100,000 requests. If you multiply these two numbers together, it means that we need to do 100 million addition operations in the worst case. So in general, 100 million operations result in a time limit exceeded error. It's usually too slow. However, in this case, since the task is so easy, it somehow passed. Caddis somehow let us do. But can we do better? That's the question. So, yeah. Here's the second. Right? Notice that we only really care about time points where changes happen. So between the first, if you look at the graphic down below, between the time when you receive the first request and the time you receive the second request, there's nothing really happens. So you don't have to worry about it. And similarly, between this line and this line, there's nothing happens, so you don't have to worry about it. And notice that every time a new request arrives, we get one more request being processed. And then every time a request finishes, we can decrement our current request counter if we have it. And this is the observation you need to make the optimization for this problem. And another thing to notice is that the maximum number of concurrent requests can only happen in the short period after you just received a new request, right? For example, right here, before this point, you have 3 requests being processed at the same time. And after this short period, before, let's say, the first request finishes, this gives you four concurrent requests, which is larger than 3. So you only need to pay attention, basically, you only need to pay attention to the short period after you receive a new request. And given these observations, I'll give you guys like 5 to 10 minutes to try and come up with a better solution that doesn't need us to do like 100 million operations. One server process. One server process. One server. Several service processes. Oh. Anyone need any clarification? I've had a decent amount of time to think about this idea and perhaps figure something out. If so, then good job. Otherwise, feel free to listen to me, and then I'll explain the second solution. So to rephrase what we want to do, basically at each request starting time, we want to find how many requests are currently in progress. And then we want to keep track of like the maximum number of concurrent requests at each request starting time. For example, at the beginning, when we first received the first request, there's only one. Well, after we receive the first request, there's only one request in progress. And after we receive the second request and the third request, we have 3 requests in progress. After we receive the fourth request, we have 4 requests in progress, and then so on and so forth. Like you would find the maximum number of overlapping requests to be here, which is 5, or here, which is 5. And then in this case, you just divide 5 by k and then get the answer. The answer you want. Now, before we go through an example, let me again talk about this problem setup. Suppose it takes 3 milliseconds to process a request. And then suppose the requests come in at t equals 0, 1, 4, 6, 8. On the left, I have it illustrated using blocks. And on the right, there's an array. There's the array storing all the request starting time. Now, initially at time equals 0. Oh yeah, we also, so for this problem, we would need to use 2 pointers, the 2-pointer method again. However, it's slightly different from the last time we used it. We would need 1 pointer pointing to the current request we're processing, and then another pointer pointing to the earliest request that's still in progress. It might not make sense right now, but it will be clear after you see a couple of iterations of the algorithm. So initially, we initialize both of these pointers to point to the first request in the array. And at time equals 0, we receive the first request, and then we can update our in progress counter to 1. The maximum number of concurrent requests number is also 1. And after processing the first, well, after we start processing the first request, we can move on to the second one. At time equals 1, the in progress counter, we can increment the in progress counter because we moved from the first request to the second. And notice that the maximum number of concurrent requests is also updated to 2. Now moving on to 4, to t equals 4. Because we just started processing third request, so we can increment our in progress counter. However, notice that our pink pointer, which is currently pointing at the first element in the array, tells us like the earliest request we received, right? In this case, it's 0. So it came in at time 0, and currently it's time 4. What does this mean? This tells us this request is already finished, since each request only takes 3 milliseconds. Therefore, we can just move our pink pointer 1 slot to the right, and then decrement our in progress counter to reflect this fact. And then notice that the pink pointer is pointing at 1 now. However, 1 is also 3 smaller than 4, which means this request is already finished as well. So we need to move our pink pointer again and decrement our in progress counter again. This gives us an in progress number of 1, and then the maximum concurrent number is still 2. Moving on, we move the black pointer 1 slot to the right, and then currently it's time equals 6. The number of concurrent requests is 2, and notice that like the pink pointer is pointing to 4, which is not which is only 2 smaller than 6, so we don't have to worry about it. And then we move to 8, the last element, the last request in the array. Now t equals 8, and we increment our in progress counter because we're processing a new request now. However, notice the pink pointer, which is pointing to the the earliest request that hasn't finished in the last iteration, is pointing to 4, which means that request was received at time equals 4, and currently it's time equals 8, so it's already finished. We need to move this pink pointer again to reflect this back, and we have in progress equals 2, max concurrent equals 2, And that concludes our algorithm. Basically, we have found that in this example, the maximum number of concurrent tasks is 2. If you look at this graph, right, at any given time, there can only be 2 blocks that are like vertical, while stacking on top of each other. And the graph also confirms that our solution worked. So here's the pseudocode for our algorithm. Initially, I'll just go through it slowly so that you understand what's happening here. Initially, we initialize M and IP. IP is our in-progress counter. M is the maximum number of concurrent requests at any given time. And then we have our pink and black pointers. Then we go into a loop. While black is smaller than request num, so like while the black pointer is still pointing to a request, we want to move the pink pointer to the right until the request pointed to by the pink pointer is still in progress. So basically, how do we check this? Can anyone tell me how can I check whether or not like this request is still in progress? Anyone? No? Okay. So basically, request pink gives us the time at which this request starts. And then at the same time, we also know black points to the request we're currently processing. So request black minus request pink is the time interval between right now and when we started processing the pink request. And if this number is smaller than or equal to 1,000, no, if it's smaller than 1,000, it means this request is still in progress. If it's greater than 1,000, it means it's already finished. And then we set IP to black minus pink plus 1. This essentially is just calculating the number of requests that is still currently in progress. And then we set M equals max MIP, comparing M to IP to see if we have more requests in progress than we had ever before. And then we increment black at the end of the loop. At the bottom, I have the C++ and Python implementation. You can take a look and then run it on your computer, run it on Catus, just to confirm that it does pass the test. Also, if you pay attention to the runtime, Catus will tell you how long it takes them to run your program and then finish all the test cases. You notice that this solution is way faster than the early one. If I remember correctly, the Python solution took me like 0.07 seconds, and then this Python solution took me like 0.07 seconds, whereas the earlier Python solution took me 0.3 something seconds, which is like an order of magnitude slower. Okay, does anyone have any question? Feel free to ask if you are still confused or like still have any questions. Okay. Now that concludes our workshop section of this workshop. If you have any questions, comments, and concerns, please fill out our feedback form at this link. We really appreciate your feedbacks, and we will try to make our workshops better in the future according to your taste.
And anything you write, we will all read and discuss. So please, just tell us anything, any single thing you want fixed or changed or you liked. We appreciate it all.
I'll give everyone like 3 minutes to do this, and then we'll move on to Kahoot. Fun part.